All right, let's dive right into this explainer by looking at what is honestly one of the most audacious crossovers in scientific history. Picture this: a brilliant, Nobel Prize-winning theoretical physicist decides to just step entirely out of his lane to crack the ultimate biological mystery. What exactly is life? I mean, it's a question that's puzzled humanity for literally millennia, right? But looking at it through the strict, totally unyielding lens of physics, that offers a completely mind-bending perspective.
I think, therefore I am. You've probably heard that before. The philosopher Descartes gave us that famous anchor for our own existence. And for centuries, we've kind of separated our subjective consciousness from the nuts and bolts, the mechanical workings of our physical bodies. But what happens when you actually try to bridge that gap? What happens when you try to account for everything taking place inside the spatial boundary of a living organism using only the hard-cold rules of physics and chemistry?
Well, that is exactly what Erwin Schrödinger set out to do in his groundbreaking 1944 text, What is Life? And the context of this publication is just fascinating. See, Schrödinger actually opens his book with a humble apology. He acknowledges this unwritten rule that a scientist really shouldn't write on a topic they aren't a total master of. Yet he felt this overwhelming necessity to synthesize our knowledge. He did it even at the risk of, as he put it, making a fool of himself by venturing completely outside of physics and into the realm of the biologists.
So, this brings us to part 1, the naive physicist's question. Why are atoms so small?
Schrödinger calls his specific approach that of the naive physicist. And to get us into that mindset, he kicks things off with a question that honestly sounds almost ludicrous. Why are atoms so small? To understand why he's asking this, we really need to look at the sheer microscopic scale we're dealing with here. That tiny fraction, 0.00000000001, that's an angstrom. It's literally the 10th billionth part of a meter. This is what physicists use to measure atoms. To put that into perspective for you, if you look at the absolute smallest grain of matter you can still just barely recognize under a standard microscope, that tiny speck still contains thousands of millions of atoms. It's wild. To really bring this sheer volume home, Schrödinger leans into this absolutely mind-blowing analogy originally devised by Lord Kelvin. Okay, picture this. Imagine you take a simple glass of water and you somehow magically mark every single molecule inside it. Then you go to the beach, you pour that glass into the ocean, and you thoroughly stir the 7 seas to distribute those marked molecules perfectly around the entire globe. If you then traveled anywhere else in the world and scooped up a random glass of ocean water, you would still find exactly 100 of your originally marked molecules in that new glass. I mean, no way, right? But that is just how incredibly small and how unbelievably abundant atoms are. So the crucial point here is flipping our perspective. The atom isn't just small objectively, it's small relative to us. The real question the naive physicist is asking isn't actually why the atom is small, but why must our bodies be so incredibly large compared to the atom? Like, why couldn't we be much smaller? Say, an organism composed of just a moderate number of atoms, sensitive enough to actually feel the impact of a single atom from the outside. Which leads us to part 2, the need for order, the physics of thought. To answer why we must be so large, just ask yourself, what would life actually be like if our sense organs were sensitive to the impact of just one single atom? The short answer? Absolute chaos. Schrödinger logically deduced that thought itself is, by definition, a highly orderly thing. Therefore, the physical organ hosting it, your brain, must be a highly ordered organization that obeys strict physical laws to a really high degree of accuracy. Think about it. If your brain were small enough to be pushed around by the totally erratic behavior of single atoms, the physical processes responsible for your thoughts and senses would just be constantly disrupted. You literally wouldn't even be able to comprehend the information in this explainer. All right, part 3, order from atomic chaos, the unceasing writhing heat motion. So this brings us to a core microscopic problem, which is atomic chaos. All atoms continuously perform this completely disorderly heat motion. They are unceasing, they're wildly unpredictable, and they are just constantly vibrating and bouncing off one another. Because of this, classical physical and chemical laws are entirely statistical. A single atom? Totally chaotic. A small group of atoms? Completely unpredictable. They simply cannot enroll themselves according to any recognizable stable laws. It's actually only when you have the cooperation of millions upon millions of atoms that the massive numbers finally average out that chaotic heat motion and statistical laws begin to operate accurately. Basically, the larger the number of atoms, the more accurate and orderly the physical laws become. To show exactly how this statistical order works in practice, Schrödinger gives a really great physical example.
paramagnetism. Imagine filling a little quartz tube with oxygen gas and placing it in a magnetic field. The oxygen molecules act like tiny little magnets, and the field tries to align them parallel, kind of like compass needles. But they don't just snap into a perfect rigid line. They're constantly being bumped out of alignment by that chaotic, unceasing heat motion we literally just talked about. It's only because there are billions of them that statistically a proportional number align with the field, creating a predictable magnetic effect. The precision we see comes strictly from the massive numbers involved.
And that brings us to our final section, Part 4, the aperiodic crystal, the carrier of life.
Okay, so we've established that physical laws rely on massive numbers of atoms to create order. But biological research shows us that the most vital part of a living cell, the hereditary material, the chromosomes, manages to dictate the incredibly complex order of an entire organism from a shockingly small microscopic space. So how can it possibly do this without relying on those massive statistical averages? Well, Schrödinger proposed something truly revolutionary to bridge this gap. Classical physicists were used to studying periodic crystals. These are structures where atoms just repeat in a regular, uniform pattern. Schrödinger beautifully compared this to a plain, kind of dull, repetitive wallpaper design. But the vital part of a living cell, he argued, must be what he termed an aperiodic crystal. It doesn't just repeat mindlessly. No, it's constructed much more like an elaborate, highly meaningful Raphael tapestry. It contains this incredibly complex, coherent miniature code packed into a tiny space that's capable of directing the entire life of the organism. It's a real game changer.
Which leaves us with the ultimate provocative question. If the secret to life isn't just large-scale physical statistics, but rather this highly intricate, non-repeating molecular tapestry, what does this aperiodic crystal actually look like inside us? How does this microscopic chromosome fiber manage to completely defy the chaotic heat motion of the universe to reliably pass on the exact blueprint of life from generation to generation? It is just a fascinating mystery of structure and survival. And honestly, it really leaves you wondering just how miraculously engineered the microscopic world inside you truly is.